From the Library of Congress in Washington, D.C.
Good morning. I'm Jennifer Harpster. I'm a digital reference specialist with the Science, Technology, and Business Division here at the Library of Congress. I'd like to welcome you to today's program, Shedding Light on Dark Matter. And in this program, we're going to learn about the ever mysterious invisible matter, aptly called dark matter, that makes up a large part of our universe. This program is a third in a series in 2010 that's presented through a partnership between NASA Goddard Space Flight Center and our division. And this is our fourth year we've been partnering with Goddard. Our speaker today is Dr. Richard Mushotzky. I just said that right. Is currently a full-time astronomy professor at the University of Maryland, and he is an expert on dark matter and clusters of galaxies. Additionally, he is an interdisciplinary scientist on the Chandra, which I've been told means light in Sanskrit, a science working group, and that's NASA's flagship mission for X-ray astronomy. And he's also a mission scientist on the XMM Science Advisory Group, which is also an X-ray mission. In addition, he's a member of the National Academy of Sciences, the National Academies, because they changed. Okay, National Academies of Sciences, Astro 2010 review. Why am I not saying this right? Mushotzky received his bachelor's degree from MIT and a master's and doctorate from the University of California at San Diego. He joined Goddard soon after completing his doctorate, but recently left to become a full-time professor at the University of Maryland. He has received numerous awards and honors for his work on dark matter, which include 3 NASA medals for achievement and a Goddard's Lindsay Award of Scientific Achievement. In addition, he has authored over 325 refereed publications and is one of the Institute for Scientific Information's highly cited scientists. So please join me in welcoming Dr. Richard Mushotzky.
Thank you so much for that kind introduction. As was indicated, I was at Goddard for many, many years and just recently have gone to Maryland. And I still have close associations with Goddard and are involved in a lot of its projects. So the theme behind dark matter essentially is, what is the universe made out of? And in that pie chart that you see, can everyone, if I point to it like this, is that okay, or do we need the laser pointer? Laser pointer, okay. So in this pie chart, you'll see that this is our best present estimates of what the universe is constructed of. Unfortunately, the large slice on the left is a thing called dark energy, which I won't really talk about unless you have questions. So let me just first say that if you have any questions, stop me. It's much better that you understand what I'm trying to say than that I continue onward. So I really welcome questions, and please stop. Then in the part of the universe that we have some hope of understanding, you'll see that there's a small segment here, the colors, which is a normal material, the stuff out of which we are made. Stars are made out of the same stuff that we are. The gas in the universe is made out of the same stuff we are. And then there's this big slice here, which is labeled dark matter, which is made out of stuff that we don't understand. It's not made out of the same stuff we are. Its properties are not well understood, and it actually lies outside of our present understanding of most of physics. So it's really quite mysterious. It's not as mysterious as dark energy, but dark energy is so mysterious that we don't understand it at all. So this is the universe. What this is the deepest image ever obtained by the Hubble Space Telescope. You're seeing objects here that go back to when the universe was very young, about 1 billion years after the Big Bang, and of course everything else that lies inside of it. Everything that your eye can see here, this space is over here. Everything your eye can see is made out of stuff that we understand. Galaxies are made out of stars and gas. And this is, our present best understanding of the universe. So, in a little joke here, if you had bothered to look up what dark matter was and you went to Google, of course, Google will immediately tell you that it's a movie. Okay? And it stars a young scientist who confronts the dark forces of politics, ego, and cultural insensitivity. I'm not going to talk about that. You then look down the next link on Google, and dark matter is a video game. Okay? And it's a big shoot 'em up, and that's not true either. It's also a book, but I'm not going to talk about the book. But I thought the book was quite interesting because it says it's one of the finest tales of modern horror. And if you're a physicist, dark matter is one of the tales of horror. In other words, it's something that not only do we not understand, but how are we going to understand it is difficult to figure out. If you're an artist, there's a nice art piece called Dark Matter, which is on display in New York. So none of these are what I'm going to talk about. What I'm going to talk about is dark matter itself. And so what do I mean? So the first step, as I've indicated, is that this is the biggest indication that there are big pieces of the universe that we don't understand very well. Or another way of phrasing that is that there's pieces of physics, of science, that we don't understand very well. As I showed you in the first pie chart, and this is simply the same pie chart, but it's just drawn in a different way, I've indicated these are the pieces of the universe that we understand, stars and gas, and together they make about a little bit over 4% of the stuff in the universe. This is the stuff we don't understand, dark matter, roughly 25% in dark energy. And essentially the name dark matter conveys what we don't know. Now this was foreshadowed by that famous astrophysicist Walt Whitman in his Leaves of Grass. And I don't know if you can read it back there, but I'll read it for you. The bright suns I see and the dark ones I cannot see are in their place. The palpable is in its place, and the unpalpable is in its place. So we had a foreshadowing 150 years ago that there were large chunks of the universe we don't understand, and we have been following up his work ever since. Now, so what are we trying to understand? We're trying to understand how much of that stuff there is, what is it, and where is it? Okay? In other words, is this just something far away that doesn't influence us? Is it something that might be close to us? Nature of. So is it a particle? Remember, what are particles in physics? They're things like electrons, neutrons, protons, things that we can study. So that's what a particle is. There are things that are perhaps well explained by our physics, and there are things that are not, and this happens to be one of those that's not. And the amount of it is obvious, how much of it is there. Now the name dark matter was given by a famous astrophysicist who is showing his predilection for discovering exciting things. His name was Fritz Zwicky, and he discovered that there was a property of the universe, which was, I'll discuss it in a moment, very difficult to understand, and he gave it this name, and he discovered this in the middle 1930s, and basically for the next 30 years, his discoveries were ignored because they were just too difficult to understand. They lay outside of the normal stream of science, and frequently that happens. By the 1960s, and I'll show you some later on, this became an object of intense study. Now, I have a not dark matter here, and I want to make clear what I mean by dark. So here you see there's lots of light from stars bouncing off of dust clouds, and the dust clouds are dark. They're dark because they're absorbing light. All right? Dark matter, we call it dark because it neither emits nor absorbs light. So I want to make sure that you understand this is not dark matter. Okay, just because it's absorbing light and we see it as dark is not what I mean by dark matter. Okay. Now, I said this is exciting. It ends up on the front page of the New York Times. This is a screen capture of one of the front pages of the New York Times. And this little story here is about dark matter. Of course, the fact that Obama solved the global financial crisis and has brought world peace is off the side. Okay. It turns out that one of the main goals of the Large Hadron Collider, and I'll show you some more later about this, is to figure out, is there a particle that is dark matter, and if so, what are its properties? Now, there was another New York Times front page article, and I like this because of the fantastic image here. This is taken in Antarctica, This is an enormous balloon, which is, when it's fully inflated, it's about 1 million cubic feet. And it's carrying a scientific payload up into the very, very high atmosphere. It goes up to about 130,000 feet high to get far, far above our atmosphere. And they basically detected something which a lot of people have interpreted as being a signal of dark matter. It's extraordinarily controversial. And by the way, am I coming through okay on this? I'm not. Oh well. Guess I don't move very far. But this also ended up on the front page of the New York Times because of its controversial nature and its possible discovery of dark matter. Now, there are other experiments that are trying to look for dark matter. NASA recently launched a very large satellite whose name is Fermi. Fermi is a very famous physicist, Italian physicist, in the middle of the last century. To get an idea, you can see the size of the human beings here. All right? This is a very large thing which was launched into space, and one of its prime goals is to search for dark matter. So NASA has thought that searching for dark matter is something very important. They're willing to spend, and by the way, the Department of Energy was a major player here as well. So here's the necessary launch site, launch picture, and this is it's up in space now for the last year and a half. This is the Large Hadron Collider, which is basically the largest scientific experiment ever built by man. Can you see the individuals here? Can you see the size of the people? These experiments are just incredibly big. This took over a decade to build, cost over $10 billion, and one of its two main goals is to search for what might be a dark matter particle. So a lot of people have spent a lot of time, effort, and energy to search for dark matter. And you can say, well, why do you have to build something so enormous in order to find this? And basically the answer is, we've tried to look for dark matter with particle accelerators before. They haven't had enough oomph. They haven't had enough energy to create what might be a dark matter particle. Remember, E equals mc squared, energy on one side, mass on the other. If the dark matter particle is heavy, and heavy means a lot of energy, E equals mc squared, you need a really big thing to create that much energy. Okay. So I'd just like to remind you that I'm talking about something that's strange in the universe that we don't understand. And most of you should say, well, so what? There's something about the universe we don't understand. How does it affect our daily lives? Well, I'd like you to think back. First of all, just define what physics is. Physics is basically the nature of the physical world. What exists, how things work, if you will. Physics has revolutionized our lives. And I mean, revolution is actually not a strong enough word. It has completely changed our lives in almost every aspect. If you go back to the era of Galileo, who showed that the Earth was not at the center of the universe, Newton, who discovered how gravity works and the nature of light. We then move up to Faraday and Maxwell, electricity and magnetism. I mean, imagine what the world would be like without electricity. Then you move forward and you say, well, Einstein, what did he do that changes our lives? Well, little things like atomic bombs and nuclear reactors and things. And then you move forward another few years and you go into the era of quantum mechanics. And basically, your cell phones, your computers, your televisions, everything rely upon quantum mechanics. So every time there's been a revolution in physics, there's been a revolution in our lives. Dark matter is an indication that there may be, emphasize the word may, be another revolution coming. I'm not going to tell you that understanding dark matter will change our lives in 50 years, but past is often prologue to the future, and it might very well. But just to remind you that physics is not something alien that's in a book that you pick up when you're a sophomore in college and put down the rest of your life. It's something that's there, and it's changed everything about your life. This is another little joke. If you go to Google and look up dark matter, you'll find out that it's a muscle-building stimulant. Okay. So this question about what physics does was asked of one of the most famous scientists in the 19th century, Michael Faraday. A British government official visited his lab. You want to see what your money's being spent on, right? And so someone asked him, what good was electricity? Because back in the 1850s, electricity just made cats' hairs stand up and things like that. And he basically said, he didn't know, but that one day you will certainly tax it. And he was right. Just to show you again the importance of dark matter, this is the front cover of Science magazine about 5 years ago. Science magazine is the premier magazine of the American scientific establishment, and it was the cover story. Okay, so just to describe what is it that we know, because we have to understand what we know before we describe what we don't know. So basically, if you have ever taken a physics course, I don't know how many of you have, but you would have learned that there is a small set of physical laws, and we have words for them like gravity, mechanics. There's not that many, and they describe basically almost everything we understand. And we have verified these laws with tremendous precision in the laboratory. Some of these laws have been verified to parts per 100 billion. These are not things that you wave your hand at and say, oh, right, it's okay. You go out and test them incredibly. Now, and therefore we have a reason to believe that we understand physics. Of course, if you go back 2,000 years ago, Aristotle had a reason to believe he understood physics also. And of course, he had the 5 elements, fire, water, earth, air, and ether, which is not normally talked about. So we have to be careful what we mean by understand, but I think it's fair to say that today there's an awful lot about the universe that we do understand and have measured precisely. So those are the laws of physics, tell you how things interact, and then we have the things of physics, the things that are interacting, okay? And basically everything we see and touch on Earth is made of, I'll use the word stuff because I can use words like mesons and protons, electrons and stuff, but stuff is better, okay? So there's a whole slew of elementary particles. They fit into a pattern which has been given the boring name, the Standard Model. One of the wonderful things and the frustrating things about physics for the last 30 years is that the Standard Model has been verified every time they tried to enormous precision. Dark matter does not live inside the Standard Model. Okay? So everything we see here on Earth, we think we understand, and therefore we expect that the rest of the universe operates the same way. Or another way of expressing that is, an apple falls from gravity and the moon moves from gravity, and Newton discovered that, and he therefore generalized the fact that gravity is a universal law. That's what I mean by we understand things. This graphic is here to illustrate that maybe this is the part of the universe we understand, and us scientists are trying to look out into the part of the universe we don't understand, and that's what dark matter is. So again, going to that font of all wisdom, Wikipedia, here is their definition of dark matter. Matter that is inferred to exist. What does inferred to exist means? We see the effects of its action, but we've not seen the thing itself. No one has grabbed a chunk of stuff which could be dark matter, all right? But you see its effect on other things. The Earth pulls the apple to fall, so that's the effect of the Earth. Of course, you can grab the Earth. So it's inferred to exist from gravitational effects. So gravity is the way we infer that dark matter exists. As you'll see in a moment, we see how things are pulled by gravity. And also radiation. As you'll see later, as Einstein predicted, gravity bends light. So we can both see the effects on stuff and light. And this is just to repeat again how much dark matter there is. So one of the things that is coming out of our understanding of the universe now, where astronomy and astrophysics is focusing very heavily, is how did the universe, let me say this morning, how did the universe that we see today come to be the way it is? How did stuff form? In other words, how did our solar system get to be where it is? How did our galaxy get to be where it is? How did the universe as a whole have the structure that we see? That is completely dependent on how much stuff there is in the universe and where it is. And as you saw from those pie charts, a lot of that stuff is inferred to be dark matter. So dark matter has an incredibly important effect on how the universe came to be the way it is. And this is a schematic of the Big Bang and everything that happened on the way to traffic jams in Washington, which we don't understand at all. Maybe that is dark matter. It certainly felt that way this morning. Okay. So the first thing is how to determine how much stuff there is in the universe. So this is the evolution of the universe from the Big Bang to today, and of course we are here. And lots of things happened along the way, and gravity had a major influence on a lot of those things. Okay, so now we're going to go to how we measure how much stuff there is. And the prime way we do it, the way that Newton taught us to do it, is to measure the effect of gravity on things. And the closest thing outside of our planet are the other planets, right? So we can measure the orbits of the planets. We can measure the orbit of Mercury, the orbit of Venus, the orbit of Earth. We can see how they rotate about the sun. We can measure how fast they're moving and how far away from the sun they are. And in the bottom left graph, you'll see a line, and you'll see the data points. This is only going to have 2 graphs in this talk. This is one of them. We'll see the line, which is what Newton would have predicted for how fast the planets would move versus how far away they are from the sun. And they follow that law almost precisely. What I mean by almost is that Newton was not fully correct about the way gravity worked. You have to add Einstein in there. And if you add Einstein in there, it's perfect agreement. There is absolutely no evidence in our solar system that there's anything other than the stuff that we understand. Just to remind you, this is top down what the inner part of the solar system looks like. The planets go around the sun in more or less circles. Ellipses, if you want to be more precise. Okay, so then we go to the next biggest thing. We live in a galaxy, and this is a real photograph of a galaxy. It's not an artist's picture. This is our nearest neighbor, big neighbor in space. It's been given the name the Andromeda Galaxy. And we can measure, you can see individual stars in that galaxy. You can see them. You also see big blobs of gas. We can measure how they rotate around the center of the galaxy in a way that's very similar to the way the planets rotate about the sun. It's not exactly the same, but I'm going to be slightly sloppy. If someone wants to ask me a more detailed question, I can answer that. So then we know our Newton's laws. We can then predict how the stars should rotate. I forgot to tell you, because we have to know how much mass the stars have. We think we understand that in great detail. We understand how stars work and how to relate how much light they have to how much mass. And then we get that red line. Then we go out and actually measure how fast the stars rotate, and we get the white triangles. Oops, something's wrong. The stars are rotating a lot faster when they're far away from the center of the galaxy than Newton told us they should, on the basis of how much mass we think is in the galaxy based on how bright it is. Okay. This was discovered, I should have gone here, by Vera Rubin, who worked at the Carnegie Institute for Terrestrial Magnetism. Her papers are here in the Library of Congress. And she got the National Medal of Science for this work. And she discovered it in the 1960s. So now for the last graph of the talk. So here's the light from a galaxy. Here's how fast we think the stars should be moving based on how much light. And then this is what we see. So what you can see is that the further away you get from the center of the galaxy, the greater the discrepancy. What that means is that there's lots of light, lots of mass, and no light further out. This is the origin of the major discrepancy between what we see and what we think we should be seeing, and it's been given the name dark matter. So the important idea number 2 is that galaxies, and remember, we live in a galaxy, the Milky Way. The Milky Way is big. It's about 30,000 light years across. It has 100 billion suns in it, so it's a big place. But there are lots of galaxies in the universe. We can do these measurements for lots and lots of them, and lots of them have been measured, and they all behave the same way. So this is the first strong evidence for the existence of something that we didn't understand, that the stars were moving in a way as if there was a lot more matter there than we could see. And I literally mean see. Unfortunately, astronomers don't have access to the other senses, like touch or smell, but we can't see it, therefore the name dark. Okay, so then we go to bigger things, and what's bigger than a single galaxy? It's a bunch of galaxies together. And our local neighborhood If you're an astronomer, a local neighborhood means a few million light years across. All right? And the Milky Way is there, and our big nearby galaxy, Andromeda, is there. This is a bunch of galaxies in one place, which we give the name to as a group. Astronomers don't like to use the word bunches. Right? So what do? We try to measure how much material there is in this group, and we use the same technique. We try to see how fast the galaxies are moving compared to how much stuff we infer. One big difference between a group of galaxies and an individual one, you see this nice little purple thing, that was on the front page of the New York Times in the 1980s. The space between galaxies, remember, let's go back here. We had, I showed you this pie chart too many times. Oh, here we go. There was stars and gas. That's the normal stuff. Okay. Stars, we know what stars are. Gas, well, we know what gas is. And so in these big things called groups, a lot of the normal stuff is gas. And gas is colored purple here because it looks nice. The stars are in the galaxies. It has no real color. Okay. It turns out that gas is very diffuse, very low density, much thinner than our atmosphere. And it turns out to be very, very, very hot. That's one of the things I worked on when I was at Goddard, trying to understand that gas. So we have two ways of measuring how much mass there is, how fast the galaxies, whoops, can you see that? It's very light on my screen. This is the galaxies whirring around. They're not moving in a plane, they're just whirring around like that. And so the orbits of the galaxies, the faster the galaxies move, the more mass is required to hold them in their place. The hotter that gas is, the more mass is required to hold them in their place. You do both calculations, there's a lot of dark matter there. Okay. Then we move on to the biggest things in the universe. And we all like to talk about the big things. The name that astronomers give to the biggest things in the universe are clusters of galaxies. What that really means is a huge number of galaxies. Every fuzzy dot you see there is a galaxy. All right? So these are unbelievably big things with huge numbers of galaxies in them. Remember, each galaxy has 100 billion stars. All right? So we have to use words to describe these things which we normally use for the national debt. Those are the only words that convey the size of these things. And I actually worked it out that the mass of one of these clusters is 1,000 million times the mass of the sun, or if you want to express this, 10 times the number of pennies in the national debt. So that's big. Just like in the groups, the galaxy clusters have hot gas in them as well, and we do exactly the same things. We measure how fast the galaxies move. We measure how hot the gas is, and therefore we infer a nice little number here with a little precision. 86% of the material is dark. Just to give you an idea of how scale these things, the galaxies are moving at about 2 million miles an hour. All right, so that's moving fast. But these clusters are so big, it takes 1 billion years for a galaxy to cross the whole cluster. So that gives you sort of an idea what I mean by the biggest things in the universe. These are just mind-bogglingly big, and they're totally dominated by dark matter. So remember I said in the definition in Wikipedia, the other way we can see the effect of gravity is on light. Einstein predicted in 1905, and it was verified in 1919, that gravity would bend light. That was, by the way, sorry, I got the dates wrong. In 1916, in general relativity, he predicted light would be bent. That was the observation. There's a whole major expeditions to go out and measure the bending of light by the gravitational force of the sun that convinced people that Einstein was right. So bending of light has been around for a long time, since 1916, but astronomers have actually used it to measure how much gravity there is. It's exactly what you think. The more gravity, the more mass, the more the light is bent. Okay? It acts sort of like a really bad lens. And so we use the word, well, the images, you'll see what the images look like in a moment. The images are not really nice. They're all curvy and distorted. but we use the word gravitational lens to describe the effect of something that's there that's bending light, right? Just the concept, more mass, more light is bent. The thing that's bending the light, we give the name to gravitational lens, and you can see what I mean by bending a light. The light ray would normally go out over there. There's this big cluster, which has, remember, lots of mass, and it's bending light so that we see it instead of the light ray going out like that. All right? This is just a better picture of that. This is what we see in nature. You notice all these very strange arc-like shapes. That's what a gravitational lens does. It doesn't cast a really good image, it casts a distorted image. What you know is when you look at these things, these strongly distorted images are the image of something in the far background, way beyond the cluster, whose light would normally go straight through the cluster if gravity were not doing its thing, and we'd see them as normal galaxies in the background. But light's being bent. Gravity is doing its thing, and so we see these very, very, very strange shapes. This is an image from the Hubble Space Telescope. The amount by which the image is distorted tells you how strong the gravity is. If you will, the prescription on your glasses. The amount of gravity that's there is related to how many diopters. Unfortunately, it has terrible astigmatism, right? So you wouldn't use gravitational lenses to see well. But they're a wonderful way of inferring that there's a lot more stuff there than we literally see in the galaxies. So given all this information about how much matter and dark matter and gas there is, if you're a clever theorist, that's a person who tries to predict and understand the way the universe is, you basically build a universe in your computer. And you then look at the properties and try to see whether those match the properties of the real universe. Oops. And given that they have this in their computer, we can fly through it. We can actually see what the theorist's universe would look like in 3 dimensions. The really small dots there are normal galaxies, and then you see these big yellow things. Those are the clusters of galaxies that I talked about earlier. And we can fly through this. We can measure its properties in the computer. We can compare those properties to the real universe, and then we can adjust things like how old is the universe, how much normal matter there is, how much dark matter there is. And what we find is that in order to have these simulations match reality, we need an awful lot of dark matter. This is, by the way, made by Volker Springel, who's in Germany, and visually I think it's pretty impressive. Okay, that's focusing on the biggest cluster they have. So without dark matter, the theorists' models in their computer, putting in all what we know about the universe, wouldn't match the universe we see. So I've gone from the solar system to the Milky Way, to groups, to clusters, and now I can go to the universe as a whole. This is a map, and I mean that in the literal sense of a map, of the nearby universe. Again, astronomers have an interesting idea of what nearby is. This is this is the universe within 1 billion light years. It has names on it. I don't know if you can read them from where you are, because just like we name the constellations, Orion, Sagittarius, whatever, we can name these big structures in the universe. Okay? People like to name things. This is color-coded such that distance corresponds to color. This big band running across the center, by the way, this is real data. This is not artist's picture or anything. This is real data. And so the band running across the center is our own Milky Way, which of course emits light, and if you have a telescope, you'll see it. Okay? So we have a combination of what's nearby and what's very, very far away. So this is a map of the whole universe. This was produced by a consortium of people, and it's been given the name 2MASS for the catalog, in case you want to look it up in the web. I thought this was a rather dramatic appearance of our understanding. However, we can go even further away, and in one of the spectacular achievements of astronomy in the last decade, a group called the Sloan Digital Sky Survey. That's the same Sloan that the Sloan Foundation is, the founder of General Motors. That foundation donated a large chunk of money to try to map the universe. And they succeeded But they couldn't map the whole sky. They didn't have had enough time yet to map the whole sky. So they mapped big chunks of the sky, which project as wedges in this picture. All right? So the fact that it's blank here doesn't mean the universe is blank. It means they just haven't gotten there yet. And so this maps the universe out to about 6 billion years. And this is an enlargement of one of those little pieces. That's, again, real data. It's not an artist's projection. And again, for this, as you saw that flyby, right, we have to match the real data. So now we have all these indications that there's a big chunk of the universe we don't understand that has gravity from stuff we don't see. Maybe it's the fact that we don't understand the law of gravity really well. I mean, why do we have to put something new into the universe? Just change our understanding of gravity. And we know that this is a possibility because we went from Newton to Albert Einstein. So why did Einstein have the last word? Physicists have this terrible need to actually check things. All right? That's what we do. And so we can try to see if Einstein was right or wrong by direct measurements. So this image is one of the most recent checks on whether Einstein is right or not. And what do I mean? Remember I talked about we can measure the gas and how hot it is, the stars. We know the stars live in galaxies, and we have lensing. We can measure where all these three components are. Where are the stars? Just look. Where's the gas? We look with an X-ray telescope. And where is the effect of gravitational lensing? That's a little bit harder to do, but we can do that as well. So we're making a map of all three colors. Each one of these things is telling us where the mass is. And what you see here in this picture is that they're in different places. In other words, the gas, which is color-coded in purple, in this particular cluster, this has been given the name, it's a wonderful name, the bullet cluster. This is another way of projecting the data. The X-rays are now in this color, and it looks like a bullet. What this is two giant clusters of galaxies that have smashed into each other. All right? This is the biggest collisions in the universe. The two biggest things in the universe, clusters, are smashing into each other. By the way, there's lots and lots of clusters, which is previous picture showed. And we can actually look at what each technique tells us where the mass is, and we can basically say that Einstein's theory is verified to fairly high precision using these data. Okay. And this is literally up to the moment. This is a press release on Friday from the Chandra Science Center, illustrating what I just illustrated with this things. And what they have shown is, again, so this is a gratuitous video, but it looks really nice. What this is a theorist's idea of how the universe was born and evolved. So the universe started as something very diffuse, and it starts to grow. Structure forms with time and grows, and that can be compared, again, with what we see. And again, we get this really nice image of what the universe should be like. But basically, the press release's title was Einstein's Theory Fights Off Challengers. So the latest data is verifying Einstein's theory to the precision that we can today. Okay, so just to remind you, as that video showed really rapidly, the universe is changing with time. If you look back in the beginning of the slides, I showed this thing, the universe starts with the Big Bang, and we are today. We can observe those things in the universe, like galaxies. They're changing with time. We go to our theorist's computer. This is a Hubble montage. Early in the universe is here, and late in the universe is there. And we can try to calculate how things are changing with time. And again, dark matter is required to explain the way galaxies are changing. Okay, so I hopefully convinced you that physicists think they know what's going on the Earth and with things we understand in physical laws. We've measured stuff in the universe which doesn't agree with that really well. We've given it a name, dark matter. We've tried to check if Einstein's theory is right or not, Einstein's theory of gravity, and as best as we can tell, is correct. So what's left? Well, we have formed a detailed understanding of dark matter. Okay. And so basically, the thing that's left is that there is, I guess I should quote Shakespeare here, there's something in our world Horatio that, someone help me out here with the last line, that's beyond our ken. And what that is thought to be a particle. And what do I mean by a particle? A neutron, a proton, an electron, which we haven't seen yet, we haven't measured, and in which none of our present theories predict. But that doesn't stop people from being extra clever. And there are wonderful people out there who are inventing new theories which produce these particles. Okay? And again, as I tried to indicate early on in the talk, every time this has happened before in physics and science, it's meant a lot of things have changed. So I would think that right now the text here, which you can read, it's a quote, is maybe the leading theory for dark matter. You know, all those socks that you've lost in the dryer, all those keys and everything else that you left behind. I don't think we can rule that out completely, but I should say that not everybody is on board for what I've told you. There are people who believe that we've done something seriously wrong. They can't figure out what it is, but they just don't like the answers. And so therefore they say this, the quote is, this is a direct quote, "This isn't physics at all, it's just fairies at the bottom of the garden." That's the minority opinion, but science doesn't work by vote. Science works by tests. And so we're now trying to do every possible measurement we can, both in space, in other words, to look at the universe, and I haven't had time to go through this. By the way, how are we doing for time? That clock's wrong. It's a quarter after 12. Is that all right?
Yeah, and then some questions.
Okay. I didn't have a chance to go through this, but there are people who are building experiments in laboratories now to look for these particles. Okay, there are very elaborate experiments, and to measure a particle which we don't understand what it is actually very difficult. But they're trying, in addition to all that stuff I showed you earlier, the LHC. So again, this is the conclusion. Why do we care? Just to remind you, every time we've done something new and relevant, new and different, it's really made a giant change in our lives. And I guess I'll stop there.
So I bet we have lots of questions, yes? We'll start with the green.
I have a really simple question. When you just said the slide before last, it said that dark matter is a fundamental new property of the universe.
Right.
Do you mean new as in new to our
Yes,
understanding?
new to our
So
understanding.
it's always been there, it's just now we're starting to
Well,
realize
actually, yes, and you actually have asked a slightly deeper question than you may have realized, because one thing would be that there was something that was present in the early universe that we don't see today, or the other way around, something that was not present in the universe that's gotten created. It turns out that dark energy has that latter property.
Dark energy was always there.
Dark energy is always there, but the amount of it has been changing radically with time. Now we have more dark energy than we had in the past, which is a concept that's very hard to comprehend. Because with dark matter, we can look at the way the universe is formed and evolved. We can go back to very early times, and we know that dark matter has always been there. So it's new to our understanding, but not new to the universe.
Oh, yeah, yeah. Oh, no, you can. I lost my phone in this.
Oh,
Dark
sorry.
matter took it away.
There, go ahead. Fell in blue.
One of the tropes of science fiction is alternate universes,
Yes?
which different things are going on at the same time. Have anyone proposed that the dark matter is the alternate universes that's going on, and that's
No.
why we can't find it?
Not dark matter, but dark energy.
Okay.
There's actually a theory, a fellow by the name of Paul Steinhardt at Princeton University has basically taken the name he gives to other parts of the universe which we can't really experience. He has a wonderful name. They're called branes, B-R-A-N-E-S. And in his theory, dark energy is caused by the collision of two of these branes together. It's very hard to check that right now.
The picture that you had of the bullet nebula, what was the observation that led to
Okay.
the conclusion about the dark matter?
Okay, thank you. I didn't have time to go through that. So it's the bullet cluster, not nebula. And it has three parts to it. So in the bottom panel shows the X-rays in sort of this orange-red. And in green, we see where the mass is inferred to be from gravitational lensing. Okay? So if there was no dark matter, it has to be something, let's call it gas and or stars, and you can see in the top picture where the galaxies are. You can see that the gas and the inference of where the lensing is occurring are in different places. So the normal matter and the stuff that's causing the lensing are in different places. All right? So that tells us that the dark matter is not gas. It's a little bit harder to see that the galaxies are the same thing. The galaxies are not where the lensing effect is. And so it's not stuff that's associated with galaxies either. Why this verifies Einstein's theory requires, I'm afraid, a considerably longer answer. But you'll have to make that leap of faith.
Start in the front, and then we'll go back over.
I have two questions. If and when we come to understand what dark matter is, will that change our understanding of all other matter?
That's an excellent question. Can I just start on that?
Yeah.
The answer is probably, and let me tell you what I mean. The way we understand things is in the context of a theory. So we understand gravity in the context of Newton, if you will. Because dark matter lies outside what we call the best theory that explains things, it has the silly name, the standard model, it has to change the standard model in a way we don't know. So that should have repercussions throughout the whole panoply, if you will, of that model. So the answer is yes.
Second short question. We're assuming that dark matter is stuff of some kind.
Right?
Why couldn't it be some other kind of thing, a force of some kind?
Oh, well, okay. That's another very good question. In the standard model of quantum mechanics, all forces are produced by particles. Okay, and particles are stuff. So there's a deep connection between forces and particles. Unfortunately, dark energy violates that connection. Okay? So everything excluding dark energy has a deep connection between force and matter and stuff. Now, you're asking actually one more deeper question, is that if dark matter is not stuff, what could it be? And I went through that a little fast, which is that it's a change in the way we understand gravity works, a change in that theory. And that is certainly a viable possibility. It's being checked right now, and so far Einstein's checked out okay.
In the front.
Could you explain what on those two images, the lensing effect and where it occurs?
Okay.
I think I got a little lost.
Right. So let's go back to the picture of lensing. So if I have one thing in the background, so this is us in the front, this is my gravitational lens, which in this case is a cluster of galaxies, and there's something in the background. And what turns out is that this is, of course, very simplistic. There's lots of things in the background. So I can measure, and that's what this is, all those things that are highly distorted or arcs are lots of things in the background. And each ray tells me how much light is bending it. So think of it as a wallpaper in the background with a really bad pair of glasses in the intermediate distance. And if I understood, which I was taught, how lenses work, I could figure out what the lens is doing by looking at how my wallpaper is distorted. In our language, the lens is not the remember refractive index? You go to the optometrist, he tells you how many diopters you are. That's what we're measuring with our regular glass lens. In this case, we're measuring the force of gravity. So that's the effective lens. Does that help?
Okay, so then can you go back to the bullet one and
Right. So
the green line?
Right. So the green lines are telling us basically, I'm sorry, you're right, I went through this a little bit too fast. Basically how strong gravity is. And these are lines of constant gravitational force, if you will. So the closer you are into the center, the more gravity there is. So gravity is strongest in projection in the center, and then gets weaker in projection as you go further out. So if you will, if this was this is telling us a map in 2 dimensions of the strength of gravity in the bullet cluster. And it has 2 fried eggs, one bit here and one bit there. And what we think that is, so I need another arm to wave wildly. So I have 2 clusters. Clusters consist of 3 components: galaxies, dark matter, and gas. One component, second component, smash into each other. Right? What happens? The gas behaves like air. You have 2 particles of air or 2 particles of water hit. They sort of tend to stop when they hit each other. The dark matter just flies right on through. And so it ends up at a different place than the gas. And the galaxies interact a little bit, not as much as gas, but more than dark matter, so the galaxies end up as an intermediate location. So this tells us that we can test our original idea that we have these 3 components, and they are behaving differently when the big clusters smash into each other.
So you like to see the big clusters smash into each other? Oh, we do have lots of questions. I guess we'll, and then we'll.
Just one quick question. What's the main thrust of investigating dark matter? Is it looking for a new particle, or is it looking for a tweak on a theory?
Okay, well, the answer is both. So if you are working in the Large Hadron Collider, or you're working with the Fermi satellite, I showed those earlier on, it's looking for a new particle. That's what they're focused on. They're looking for signs of a new particle.
Is it on the, between neutrons, protons, electrons, quarks,
Right.
strings?
So I can give you names. So I'm going to give this name. It's just so neat.
Yeah.
Okay. WIMP. WIMP. And it stands for Weakly Interacting Massive Particle. That is one of the 3 best concepts of what a dark matter particle would be. Okay? And with that name, it has properties. So massive particle means it's really heavier, much heavier than a proton. Weakly interacting means that electricity doesn't affect it very much. The effects of gravity and charge don't affect it very much. It interacts weakly. In other words, like you may know a bit more, so I'm going to use another word. The way neutrinos interact, they tend to go right through things.
Right.
So that's what that particle would be. But it'd be much, much, much heavier than a neutrino. Another, since we're into names, another name, which again, physicists have to have a quirky sense of humor. The other name is an axion. Axion. I remember a few years ago. Not, yeah. And AXION. And that was invented about 20 years ago to solve a totally different problem in physics. All right? So it's not ad hoc just to make up dark matter. And again, the axion has certain properties. It turns out to be much lighter than a WIMP, but to interact more strongly. And if dark matter are axions, then people are looking for them by having detectors that are in deep underground mines to get rid of everything else that might be coming from the universe. Just lots and lots of rock stop everything else, except these guys. They go flying through. So you need a really, really big detector, and you just wait until something hits it that you don't expect. And this was in the newspaper just a few weeks ago, and these guys have been running this. Well, there's been several people doing these experiments. This one's been running for 3 years. In 3 years, they had 2 things hit this giant detector that weren't what they expected.
Just 2 quick questions. What are those green lines called? And do you know, is the amount of dark matter, is it constant?
Okay. So the green lines are called, they're called contours of constant surface mass density, how much stuff there is per unit area. So the contours, isocontours, sometimes you've read them called isopleths if you're making maps. If you're looking at maps, they're contours of equal altitude.
I didn't know if there's a specific name.
No, they're just that's fine. Yeah. Yeah. Actually, if you look at a map of the Earth's gravity, they're called contours of equal gravity. One of the things that we can measure is the gravity of the Earth to incredible precision, and changes by a little bit from place to place. And so they're contours of equal gravity. There's no special word. And next.
The second question, if we knew that the amount of dark matter was constant.
Ah, okay. So there's two ways of being constant. Constant with place and constant with time. Okay? Constant with time, yes. Oh, sorry. Constant with time, yes. Constant with place, no. Because in our solar system, we see no evidence for dark matter. All right? But when we go to the next biggest thing, our galaxy, we see lots of evidence for dark matter. So dark matter, that's a big clue as to what it is. Dark matter, for whatever our solar system has not been able to hold on to the dark matter. It's not, if you will, connected to the solar system, but it's connected to the galaxy as a whole. When you get to things that are as big as the galaxy and beyond, then we have more or less constant amount of dark matter. So it's only on smaller things like the solar system that we see differences.
Go, weren't you, and then we'll jump back over there.
Oh, there's a lot of
I
questions.
told you, I knew it was going to be a lot.
So based on our understanding of the amount of matter, what's the current theory about the eventual fate of the universe?
Okay, right. Okay, so if we ignore dark energy, I'll get to this in a moment, then the universe will keep on expanding forever. Dark energy does something worse. It's making the universe accelerate apart even faster. It operates like anti-gravity. So if dark energy is what is now, I'll call it guessed to be, then the universe will accelerate, expand forever, and be expanding so rapidly. Again, physicists have a funny sense of humor. They've given it the name the Big Rip. Matter would literally be torn apart. Everything would fly apart from everything else, including atoms. All right? This seems unlikely, which means that our present understanding of dark energy is almost certainly wrong. But yes, the universe will expand forever if this is correct. I'm going to give you a number. I'm sorry, but okay. So there's a number which is given the Greek symbol omega. If that's equal to 1, then the universe is exactly balanced. It will neither expand nor contract. If we ignore dark energy, the amount of material we actually measure is omega of about 0.25. So the universe will just keep on flying apart. Does that help?
If the universe is expanding and everything is moving away from everything else, how is it that these clusters are colliding?
Okay. So I was hoping that movie would convey that, because the movie is static. Okay, so this is flying through the universe. This is a shot at one given time flying through the universe. So how am I going to describe this? Okay, so the universe is expanding. This is, like I said, a static picture. But things are moving with respect to each other. It's not just a smooth flow with everything flying away. There are random motions in the universe. And so with those random motions, it turns out that on average, so I could be like a traffic cop and say what the average speed is, a cluster is moving at about, use metrics, because I can't transform to miles per hour fast enough in my head. Clusters are moving at about 1,000 kilometers a second with respect to each other. That's the random motion in the universe. So think of a big, smooth expansion, and then inside that, there's stuff moving around in a random way. And every now and then, if you're big enough, you'll hit something, because there's always something. If you're big enough, there's always going to be something you're going to hit. And every now and then, you'll hit another really big thing, and that's another cluster. All right? Turns out in the history of the universe, in the last roughly 10 billion years, your average big cluster has hit another big cluster half the time. Half of all the big clusters have hit something else that's big in 10 billion years. So it occurs, but it's not very common.
One of your slides said that there hadn't been a significant, discovery on the order of Einstein's theory of relativity for about 70 years, and it will affect society. Assuming that at some point there is a very good understanding of dark energy and or dark matter, what areas of society are there ideas that this will affect directly, whether it's religious or whether it's technological or any at all?
I wish I could answer your question. You've asked an enormously deep question. If I could answer your question, I might get the Nobel Prize soon. No, I don't want to minimize it. It's actually an incredibly deep question. And that's what, it's like the combination of, well, let me take a step back. When Michael Faraday and James Clerk Maxwell figured out what electricity and magnetism was, before they did that, nobody had any idea of what it was and what the effects it would have. That's the size. When I used the word revolution, I said that's not a big enough word. So not only do you know it will change things, you don't know what it will change. So it's a giant step. And so I don't even want to speculate on what might happen. I mean, I don't want to minimize your question at all. I want to do the opposite. I want to emphasize how important it is.
I think we're sort of running out of time
And throat.
Might entertain more questions afterwards. I mean, we have time for maybe a couple more.
I was wondering, is sound a relevant measure in this topic?
Sound. Well, not exactly. Okay. Not really. It's sound. It's a long answer. The answer is not really.
Oh, we'll do two more.
Okay.
Since this seems to be the last
Since
answer.
dark matter has a gravitational effect, if at CERN they do successfully discover the Higgs boson, does that have any impact on as far as dark matter?
It might, but I want to separate that. So in the standard model of particle physics, the Higgs boson is the particle that allows mass to exist. Now, I don't want to sound philosophical. Let me explain. The electron is the particle that allows electricity to exist. So it's not a strange concept. We've known about electrons all the time. So the Higgs particle is the particle that allows mass to exist. So it is, in the standard model of quantum mechanics, is a necessary thing and would sort of complete the theory. It may, if the mass of that is detected and its properties are detected, may be an indicator as to what dark matter is, because dark matter has mass, but the theory doesn't allow us to make that projection. It would be an experimental discovery.
Okay, one more.
I guess I had a two-part question. The first is, in looking for dark matter, why aren't black holes, say, a leading explanation?
Okay, that's...
And the second one is, if we're 10 billion years old as a universe, if dark energy is correct, how much more do we have left to go before we're...
Okay. I don't remember the latter precisely, but I think the number is about 80 billion years, the big rip. Black holes. Okay, so that actually was one of the leading ideas as to what dark matter could have been until about a decade ago. The problem, so dark matter we know has been around since, actually, we've known dark matter exists since the universe was a mere 300,000 years old. I can tell you how, but accept that for the moment, all right? Black holes, therefore, have to have two things. They can be created in the Big Bang, or they can be born since the Big Bang. Well, they can't be born late because we know dark matter existed 300,000 years after the Big Bang. So it has to be created in the Big Bang. We don't know how to do that. So theoretically, it's difficult. What about observations? All right. If the black holes are really big, then they have observable consequences, and we've observed the universe well enough to know that it can't be filled means enough to make the dark matter. Really big black holes, I'm going to use a number here, I apologize, 10 million solar masses and bigger. If the black holes are much smaller, then their observable consequences are much more difficult to infer, and we really can't see them until they get really small, things that are about the mass of the sun, in which case, believe it or not, they evaporate with time. So the universe could in principle be filled with black holes with just the right mass, but then we don't know how to make them, and we don't know how to have just the right numbers. So they'd have to be in this nice little box, which we don't know how to get there. So it's not a crazy question at all. Need some
We'll
more water.
have to bring you back.
Okay.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.